Okay, let's start. Okay, so did anyone understand this equation? Although I haven't looked at it carefully, but so it's a little bit about the linear algebra, but let's see. So ht to ht plus 1 is going through the linear combination of w or u here and maybe 10h, right? And then so this is basically a vector, right? So suppose it is a three-dimensional vector, right? And then at this point the output will be u and ht and 10h, right? And then so for this in terms of a backpropagation, so we would so let's think about the gradient vector dh t plus 1 and df. Okay, so it is this three-dimensional vector that is associated with each of these dimensions, and then these values are multiplied first with the slope at that corresponding activation value in the 10h graph, or the slope, right? So if it was 3 and negative 0.3 and maybe 2, and then we would consider like this value which is the first dimension of the gradient at this ht plus 1, and we would multiply the slope with this guy, right? And then at negative 0.3, and then we would multiply this slope with this value, right? So that is the gradient at this point, right? And then it will still be three-dimensional vector, right? Which is element-wise multiplication with this vector and the corresponding slope values, which are also three-dimensional, can be represented as three-dimensional vectors, right? And so up to this point, suppose we obtain the gradient at this point, and then what is the gradient when backpropping this linear layer? So as we discussed, and also as we saw in the maybe first problem of our exam, so it will be u transpose, and suppose this one is dy and dx, and this dx is represented as this guy, right? And more exactly, I personally don't like to represent the gradient as that one, because this one really means dy over df, right? Not this dy, right? Which is in the place of a denominator. And so we obtained this vector corresponding to here. Then this vector is multiplied with the u transpose, and that will be obtained as our gradient vector at dx or dh, right? So why do we have a diag here? Yeah, so I thought it's a little bit non-trivial, but it seems to be quite trivial. The reason why we have a diag here is because we would multiply over here with this gradient vector at the ht plus 1, right? And then suppose this slope vector was 0.01 and maybe 0.2 and 2.1, for example. And then this guy multiplied with this guy, the ht plus 1 df, which is a three-dimensional vector. So we have to perform element-wise multiplication, right? And that element-wise multiplication can also be represented as this guy, yeah, made as a diagonal element, and then vector multiplication, right? So that's why we have a diag here. And still, when multiply this one with this diag one, and that will perform element-wise multiplication, and then resulting in a particular vector, yeah, at this point, and that point is corresponding to here, and then which will be further multiplied by U transpose. Okay. And then, yeah, I'm gonna skip the explanation about the gated recurrent unit and the LSTMs. So one point, although you may already be familiar with this difference, but the main difference between the GRU and LSTM is that in the GRU, in the LSTM, we have a cells and hidden state vectors separately. In the case of GRU, we have a hidden state vector, and then the cell is containing more broader or more kind of a complete information, and then HT, it can be viewed as like the immediate information that we need in order to generate the output. So here, after doing the 10H, we filter out or we hide selectively some part of the information contained in the cell, right? And then in the case of GRU, we have integrated it into a single cell vector, so we have no longer the differentiation between the cell and the hidden state vector, but still we need to have this, this kind of output gate, so that we can hide or filter out only the necessary information that we need immediately for generating the current time steps output, right? So we need this kind of output gate, and that is kind of corresponding to this something called the reset gate, right? Reset gate. So you can view this hidden state vector as the cell state vector in the LSTMs, and then this thing, after doing this filtering operation by doing this gating one, and that can be viewed as this hidden state vector. But here, as Chris Manning mentioned, the time step of doing or performing this filtering is different between these two. So we have a current cell state, and then in order to generate this, in order to generate this current hidden state vector, we do or perform this filtering of doing this output gating at the current time step. But in this case, we have a previous hidden state vector, and then perform this gating in the previous on the previous time steps hidden state vector. So it can be viewed as like doing this filtering of this output gate on this previous time step. So yeah, he mentioned as doing this output gating on the current time step and maybe in the previous time step. Okay, so I'm not sure how much it is meaningful, but that's the one non-trivial difference between them, other than having a single vector h instead of two different vectors of h and c. Okay, so if you have any questions, yeah, feel free to stop me and let me know. So when doing the initialization of this RNN or LSTMs or GRUs, so as one of the quiz question mentioned, one thing to note is that we initialize this forget gate bias values as close to 1s. Okay, so it means initially we don't want to forget the previous time steps information, right? So let's see. So as discussed in the class, this one or this one is the main, the most important equation in the LSTM, or behind the success of the LSTMs or GRUs. And the reason is because we have this previous time steps information, right? And then we apply this kind of a forget gating, right? And then we want to have this value as close to the value close to 1, so that this guy can be propagated as a non-trivial value, which is not close to 0, to the further time steps. So in that case, when doing the backprop, because this forget gate is close to 1, the gradient signal can be backpropagated through the longer time sequences in the past. And then also this guy should be initialized to be close to 1, right? So, but other than that, all these coefficients for these linear combination matrix or linear transformation matrix should be initialized to be close to 0. And why is that? If they are initialized to be relatively large numbers, and then basically this one, as we saw in the previous example, we have this matrix multiplication, and then we have some vector, assuming that the input and output nodes dimensions are the same. And then if these values are large values, and then summation of the inner product, or the product between these three pairs and their sum will be likely to be away from 0. So in that case, when doing this nonlinear transformation of using tanh or sigmoid, these values will be kind of likely to be saturated value, so that the gradient is becoming close to 0. So that way, when doing many of these multiplications and adding them together, those values should be sufficiently small, so that the output after doing this sum of these many products to be remaining as 0, or remaining close to be 0. So that way all the other linear combination ways should be initialized close to be 0. So it is doing the typically the initialization is done by sampling, or randomly initializing by sampling some Gaussian random variables with a sufficiently small variance value, right? And then related to that, so you guys know how, I'm not sure how to pronunciate it, but the He initialization or Javier initialization or Xavier initialization. So these are also related to these number of summations of those many numbers of products, right? So in that case, the main point in these initialization techniques is that we have to reduce the value of the variance in proportion to the inverse of these dimensions or the input nodes, right? So suppose our we consider some sigma value as, for example, 1. So suppose this one is like some kind of a hyperparameter, and then this value, when sampling or doing the random initialization on these, and then each of these values should be sampled from the Gaussian distribution with this amount of a variance. So we have to reduce the variance when sampling these values because they are added together, and then their variance will be like added together, right? So when having like 3 different independent random variables, and then their variance will be the sum of 3 random variables, right? So I think it's this guy, right? So when removing it, and then it can be represented as this guy, right? I mean, assuming that these x1 and x2 are statistically independent, right? And so the variance will become large, and thus we have to use a smaller variance correspondingly in order to make these values remain around 0 so that we can avoid the saturation of these nonlinear units. Okay. And then as the quiz, as in the maybe second problem in the quiz, which is about the dropout strategy in the RNN. Suppose we have this kind of RNN structures, and this is the layer 1, and then suppose we stacked another layer, and then still horizontal direction is corresponding to the time step, and then the vertical is corresponding to the layers. And then here we do the dropouts on the, layer-wise. So for example, what is the dropout? So when having the activation corresponding to this hidden state node, maybe H2, and then we randomly make it as 0. So that is the dropout strategy in the training process. And then we make it as 0, and then give it to the next layer. So we do this kind of dropout, but we don't do dropouts. And and also this so it's more exactly if H2 has the 3 dimensions, and then we with some fixed ratio or some fixed probability, we randomly drop out like dimension-wise separately, right? So some dimension values will be dropped out or resulting in zeros, or some other values will remain as the original value, which is non-zero value, and then they will be fed into the next layer. But we don't do the dropouts to when they are fed into the next time sequence, like RNN module. So we don't do dropout horizontally, but do dropout typical dropouts on the vertical or along the different layers. And the reason the reason why we don't do the dropout horizontally is because when doing the dropouts, suppose we stored some important information generated in this time step. Suppose it was H1, and then that value was 5 when considering the cell state value. And then suppose this information, for example, when doing the character level RNN, it was like the dimension of storing. Storing the fact that we opened the double quotation mark, and then we have to close it by remembering it until we actually close it. And then we have to remember this across the long sequence, right? But if we apply the dropouts, and then dropout will be applied at this time step, and then suppose this one was fortunately surviving, and then it has to survive at the next time step and the next, and so on. So in that case, as Chris Manning said, almost all the dimensions will not be able to survive across many different time steps when those informations are needed across a long time sequence. Right? So we don't do usually dropouts along the time steps. But there are some additional techniques that we can apply the dropouts along the horizontal or time steps. And one of the methods is called what? Does anyone know the name of the dropout technique that we use when doing the RNNs? Horizontally. Don't know. How does it work? Do you know? Right. Yep. Okay, so the student gave a right answer. So I'm not sure if there is any other dropout techniques applied in the RNNs, but let's see. So oftentimes, it is hard to believe that these techniques have been around for a long time, but it was just published only last year. So this one is the benefit of the archive, I think. So I think one picture worth 1,000 words. So this is kind of this is the zone out strategy or technique. So the main idea is that it is applied to the LSTM cells because we don't pay too much attention to the original RNN because that will not be used anyways in many in almost any applications. So in the case of a LSTM structure, we have a previous cell state information. So suppose we have a 3-dimensional vector as a previous time step cell state vector, and then it will go through this kind of thing. Applying the forget gate with the previous cell state information, and then adding the input gate with maybe the new information, right? So this is how we update the current cell state information, right? And then what do we mean by the dropout? So in this case, the dropout is considered as doing or skipping this kind of this kind of updating rule. So instead of removing some information in our previous cell state, we actually skip this kind of processes that we have to do, and then we just give it to the next time step. Okay, so in this case, so it can be viewed as like setting it as 0 and setting it as 1, and then we will just deliver the previous time steps cell state information with no changes to the next time steps information. So we randomly do or we randomly skip this kind of RNN cells when processing or transforming this previous cell state information. So that is called a zone out. But I'm not sure how often it is actually used. Does anyone have an experience of using it? Do you know how often we use it? So usually we don't use it, right? It's not standard to use it, right? But we usually use the dropouts vertically when doing the RNN or LSTM applications. So dropout is, dropout is an optional technique that we can either use or not, right? But typically, in most of the neural nets, including CNNs, RNNs, and fully connected layers, this dropout is a kind of default choice that you will likely use. And also in this case of an RNN, the vertical dropout will also be used usually, but in the case of a horizontal dropout, including this zone out, it's not a standard one that we often use. Okay, but it's it's something good to know, I think. Okay. And then all these zone outs and dropouts are viewed as a regularization technique, right? And regularization means that, without compared to the case without regularizations. When using the regularization, how is the training error? Is it worse or better when using the regularization? I mean, for the training data. The training data will become worse when using the regularization. Although we can also think of, so in the case of an L1 or L2 regularization, that is actually part of our objective function. But we usually consider the objective function value or the loss value only corresponding to the training data loss, right? With respect to their ground truth labels, right? So when only considering that term in our total loss function, and then when using the dropouts and any other regularization techniques, these training error will go up or will become worse, right? But the main advantage of using this is because it will actually improve the test performance, right? So like, suppose we achieved 95% of an accuracy in the training case, and then in the test case, it only performed 80% of an accuracy. But when using the dropouts or any other regularization techniques, and then it will go down to 90, but this value will be actually increased. Okay, so in that sense, it is also a regularization technique. But in the case of an L1 or L2 regularization, we explicitly add that term into our loss function, right? So that is explicitly part of our loss function. But in the case of dropouts, it is viewed as kind of heuristic method that is not represented directly or explicitly as part of our objective function value. Okay, and then these ensemble methods are quite often used, and also it is also viewed kind of a regularization technique in a broader sense, because that will increase our test data performances, without explicitly increasing the training data performance. So so Chris Manning skipped a detailed explanation about it, but I need to teach you guys, so I thought a little bit more about how these work. So let's think about how each of these strategies will work in terms of in the context of this ensembling of multiple models. And then let's look at the first one. How does it work? How does it work? Suppose we consider like very simple character level RNN, like H, E, L, and the output should be E, L, L, and so on, right? And then, so we build the two different model so that we can do the assembly on. Then, right? Then, so we add a little bit of a variation so that those two models deviate from each other. We want to have these two models different from each other. With the different parameters learned. And then when doing the test time, how do we aggregate the or utilize both of these models' outputs? So in the case of first one, yep, I think. Yeah, so as an output, it will generate the softmax vector, right? As a kind of a sum to one kind of probability over our dictionary. So if we consider HELO as our dictionary, and then the dictionary size will be 4, right? And so it will generate the 4-dimensional sum to one vectors. And this at this time step and in this time step from these two models, and then. Yeah, we do this addition. So yes, let's suppose the dictionary size is 3, and then suppose the first time steps output is like 0.7, 0.2, 0.1, and then the second one was 0.3, 0.2, 0.5. Okay, so in this case, we just simply do the average between them. Okay, and then from that average, we do the argmax. Okay, we do the argmax. Okay, and then that case is almost identical to another strategy of this majority voting scheme, or represented as an average between the among the outputs or this kind of output vectors from different models. Okay, so in this case, what's the difference between this second strategy and the first strategy? Did anyone notice between the difference between them? 네. 내가 대충 추측을 해서 뭔가 차이를 이해했다고 생각했는데 오류가 있는데요. 모르겠네. Okay, so my initial very brief thought or guess was, so we do this averaging thing in order to generate the final output, right? The final output will be a specific kind of token selection by doing the argmax on this aggregated or averaged softmax vector. But then we can maybe utilize that averaged vector as a new hidden state vector new common hidden state vector for all the different models that we are doing the ensembling on. So yeah, in this ensembling kind of strategy, there is a notion of like early or late fusion of these ensembling thing. So what if we do the ensembling on not at the stage of an output vector of a softmax vector, but at in the middle stage. So for example, so we have a softmax vector summing up to 1, right? But we will have a hidden state vector, right? So suppose this one is the first model's output, and then first model's a hidden state vector, and then the second model's hidden state vector at the same time step t1. Okay, so in this case, suppose we are doing the average at this moment by using these two instead of doing the average all the way at the output layer. So in that case, we can do the output or the averaging kind of operation on these two hidden state vector, and then we obtain one average single average output, the hidden state vector, and then we will utilize it into, we will utilize it to feed it into the next layer in different models. Okay, in different models, and then the output will be different, right? Because their coefficient that will generate the output vector from the hidden state vector will be different because these two are different models, right? And then when using these two vectors and feeding it to the next layer, or next time step, and then we can either choose, or we can either use its own vector before doing the average, or we can use the average vector when passing it to the next time steps. So in that case, these average vector will not only be used to generate the output vector on different models, but also it can be used as actually, it can be used as a average vector to be passed into the next time steps. So the different strategy alternatively could be to just use its own hidden state vector. So that was my unsupported theory, or guess, but I'm not sure how it makes sense, how much it makes sense. But anyways, so we can do this kind of averaging thing by for our ensembling purpose. Okay, and also this ensembling can be also done not at this output, softmax vector, but at the state, at the more kind of later layers. For example, so in this case, suppose this one is HEL and HEL, and then suppose we just pick up the argmax, the token that is corresponding to the argmax entry, which is H and L. So in that case, suppose we have 3 different models, and then 2 of these models generated these 2 times of an H, and then 1 times of an L. So in that case, we can truly do the majority voting after discretizing these values into a single outputs. Okay, so that is kind of a latest possible fusion of these outputs from different models. Okay. So in this case of doing the average on this softmax vectors, so we are doing this kind of fusion or ensembling a little bit earlier than that, right? And then such an ensembling can be done kind of even earlier than that, right? Doing this averaging on this, doing this average on this hidden state vector, which is an early stage. Okay, and then also. So you got the idea of the average of these hidden state vectors, and then what are the differences between the two, majority voting and the consensus building scheme? I actually don't have much idea about what these mean, but what do these or and and means? So simply, this one is arithmetic mean, and this one is geometric mean. Okay, so in this case, so when doing the average between these 0.7 and 0.3, the average one would be 0.5 when doing the arithmetic mean, right? But when doing the geometric mean, we do the multiplication and then take the square root of it, right? And then this square root is called the AND operation, and in contrast, the arithmetic mean is called the OR operation. So I thought about why. Okay, I thought about why those two have these two different names, and then I figured that like this way of an averaging will be small. Yeah, will generate a smaller value than this typical or usual mean of an arithmetic mean, right? So in that case, yeah, suppose out of maybe 3 models, only one model gave really high score on a particular dictionary. I mean, token of an H, for example. Suppose this one is 0.9 and then this one is 0.2, and then it means that although one model thinks this value really highly likely, but all the other models are thinking that this value is not very likely. So in that case, yeah, we are kind of doing the AND operation, because if at least one of our model thinks this output is not very likely, and then it will be considered as non-likely kind of output, right? Because the overall probability after doing this geometric mean will be, I mean, remaining as a small value, right? I mean, compared to the arithmetic mean, right? So in that sense, it can be viewed as this AND gate, so that all these models should generate relatively large values. Okay. 네. 아, 네. 네. 양상분리를 어떻게 하는지는 사실 나도 잘 모르겠어요. 그러니까 이걸 가지고 막 사람들이 막 되게 많이 파고 이러진 않는 것 같고, 그냥 이거는 단순히 이제 에버리징을 뭐 이렇게 또 할 수 있고 저렇게도 할 수 있다. 그리고 이게 컨센서스 빌딩이 네, 완장일치네요. 네. 그래서 이게 하여튼 모두가 다 그게 높다라고 생각을 해야 그게 아웃풋이 그게 나올 거다라는 건데, 근데 하여튼 이게 뭐 되게 다른 건 아니고 하여튼 약간의 차이만 있을 뿐인 것 같아요. 그 산술 평균이냐 기하 평균이냐 이런 어떤 네. 크지는 않은 차이만 이제 존재하는 것 같고, 일단은 근데 하여튼 중요한 거는 이제 뭐 이런저런 뭐 특히 뭐 NLP나 이런 쪽 태스크들의 리더보드에 가보면 다 이제 자기네 모델 이렇게 해갖고 자기네 뭐 성능 뭐 한 지금 블루스코어 한 30 나와서 자기네가 뭐 한 10등 했다. 항상 그 모델의 앙상블 버전이 또 있어요. 그래서 걔네의 등수는 이제 보통 몇 등 더 높아요. 좀 퍼포먼스가 좀 더 좋고. 네. 그래서 하여튼 보통 모델 하나 만들면 그걸 이런 식으로 이제 앙상블링을 하되, 둘 중에 뭐 어떤 앙상블 아니면 이거보다 뭐 더 어떤 복잡한 어떤 팬시한 버전의 앙상블이 있는지 모르겠는데, 네, 하여튼 앙상블링을 하면 뭐 거의 모든 경우에 이제 성능이 조금 더 좋아진다. 심지어 뭐 그 CS231N에서는 여기서도 나왔나? 몇 퍼센트 오른다 그러죠? 네? 네, 2%. 2% 항상 오른다고. 어디서 나온 숫자인지도 모르는데 항상 2% 온다. 2%. 명확한 숫자까지 제시를 해주면서 그러더라고요. 근데 뭐 대충 한 20은 다, 20 정도 올라져 있는 것 같아요. 많이는 아니고. 근데 이제
근데 만약에 그냥 하나의 모델만 썼을 때에 이미 그 태스크에서의 어느 정도 수준 이상의 그런 오버바운드를 도달했을 때 앙상블이 특허가 있을까요? 이중에 오버바운드를 좀 찾다고 좀 이론적으로 하시지.
네. 잘 모르겠어요. 그러니까 이게 우리 모델이 충분히 플렉서블하고 그러니까 어떤 뭐 하여튼 펑션 어프록시메이션 관점에서 우리 모델이 뭐 한 100차원을 가지는 아니면 뭐 모델 클래스가 굉장히 이제 크고 캐파시티가 크고 그런 경우 이제 데이터도 촘촘히 모든 부분의 어떤 그 쉐입이나 그 곡선 같은 것들을 다 복원할 수 있게 데이터도 촘촘히 다 이렇게 충분히 주어지면 사실 싱글 모델의 퍼포먼스가 뭐 이렇게 앙상블이라고 해서 더 올라갈 이유가 없을 것 같긴 한데 데이터가 부족해서 모델을 충분하게 플렉서블하게 만들면 기본적으로 이제 오버피팅이 발생을 하거나 그걸 방지하기 위해서 좀 덜 플렉서블한 모델. 그래서 우리 데이터를 충분히 다 설명은 좀 하지는 못한. 그냥 이게 뭐 기본적으로는 우리가 뭐 대부분의 머신러닝에서 이렇게 뭐 트레이닝 애큐러시를 뭐 100%로 이렇게 달성을 하고 이러는 거를 오히려 이렇게 좀 피하잖아요. 그러니까 그런 측면에서 우리 모델 자체도 이렇게 너무 투 플렉서블한 모델을 쓰면 뭐 하여튼 하이 베리언스 뭐 그런 상황이 돼서 그런 경우를 좀 또 의도적으로 이렇게 방지를 하기 때문에 뭔가 하여튼 모델의 컴플렉시티 아니면 플렉서빌리티는 데이터를 다 설명하지는 못하도록 이제 하되 그것들을 좀 여러 개를 써서 이제 좀 이런 어저러티브 호팅에서 좀 이렇게 올라갈 수 있도록 하는 여지를 남겨줘야 뭐 실질적으로는 뭐 테스트 데이터에 대한 성능이 더 올라간다 이런 게 아닐까 싶은데 근데 뭐 일단은 앙상블을 써서 안 오르더라. 그래서 앙상블이 별로 좀 내가 다루는 애플리케이션에서는 별로 동작을 잘 안 하더라. 이런 류의 불평을 많이 보지는 못했어요. 그래서 그냥 제너럴 컨센서스, 여기서의 컨센서스랑은 좀 다르긴 하지만 하여튼 일반적으로 알려진 뭔가 상식이라 그럴까, 일반적으로 알려진 설은 앙상블을 하면 그냥 이견의 여지 없이 그냥 무조건 뭐 조금은 오른다. 그러니까 좀 정설인 것 같아요. 또 있나요? Any other questions? Okay, so in conclusion, I'm not sure which method is more preferred, but I think both works well, comparatively with each other. Okay. And this Lieb reading paper, I think it came out around a little bit more than a year ago. I believe so. And it was considered as quite a surprising kind of application because it actually surpassed, the performance of this deep learning based model actually surpassed, or is actually better than the human performance. In this task, machine performance is clearly better than the human performance as shown in the table. Okay, and if you imagine, if you think of like ImageNet case, and then in order to, it's now like beating the human performances when using this machine learning or deep learning models, and thus I think that's why I believe that's why ImageNet is no longer open. It just it is terminated. It is no longer be held. But anyways, in this, it took a lot of years, like maybe several decades at least, and still the human performance and the machine performance is relatively small in the case of an ImageNet classification task. And also, it is a little bit debatable in my personal opinion. Because if humans are, if we bring or invite really expert humans that knows really all the different species of frogs and dogs and cats and so on, and then I think such an expert humans may beat still the state-of-the-art deep learning performance, maybe including DenseNet or ResNet and so on. So it is kind of debatable whether the machines actually beat the human performances in the image classification task. But in the case of this lib reading, it's no doubt that the machine beat the human performance, and so yeah, it was quite impressive kind of an application of using deep learning. Okay. But I think the model doesn't seem to be really interesting. It's just a straightforward application of attention-based sequence-to-sequence model. And then, although I'm not very familiar with this notion, but this curriculum learning is one of the emerging topics. So, I mean, in many of the reputable conferences, although there are not many papers yet, but people consider this as one of the emerging area where there are available low-hanging fruits for your publications. Okay, so yeah, in this curriculum learning, I mean, the basic notion is instead of teaching the complex task immediately from scratch, we just teach like a relatively simple task first, and then later on, I mean, as the model gets trained a little bit more, and then we give a little bit more sophisticated training examples and so on. And the benefit from doing so is like a faster convergence or better accuracy, or maybe avoidance of these overfitting. But I'm not very familiar with it. But because as I mentioned, because this one is potentially kind of a low-hanging fruits for your own kind of applications or publications in your career. So it may be worthwhile to look at. Does anyone know a little bit more about it, or anyone doing the research closely related to it? 뭐 좀 아는 사람 없어요 혹시? 써본 사람?
메모리 관련 그래서
네.
보통 긴 문장 같은 걸 학습하기 어려워서 짧은 거 먼저 학습을 하고 이제 점차 늘려가는 식으로 하는 거 같아요. NTM 같은 경우 카피 테스트를 커리큘럼을 많이 하는 걸로 알고 있습니다.
네, 좋은 포인트네요. 그러면 그게 버켓팅을 한 다음에 그냥 그 짧은 것부터 이렇게 넣는 거예요, 배치를?
그 맥스 랭스를 점점 이제 늘려가는 방식으로 하고.
네.
그 맥스 랭스 이하로 이제 샘플해서 길이를 샘플해서 그걸 이제 학습합니다.
맥스 랭스 이하로 샘플링을 한다?
네. 이 랭스까지만 이 배치에서 나올 수 있다. 그런 식으로.
네.
길이 10짜리, 길이 100짜리, 길이 1000짜리.
그러면 길이가 2, 8, 3, 4, 5, 6, 4, 3, 5 이렇게 있으면 이게 이 소팅하면 2, 3, 3, 4, 4, 5, 5, 6, 8, 5 거의 눈으로 내가 N로그 N의 스캔 비슷하게 했는데 네, 어쨌건 이렇게 소팅을 하고 그 다음엔 랭스를 3으로 맥스 랭스가 3 이하다.
네.
그러면 2, 3, 3, 이 중에서만 배치를 구성해요?
그렇죠. 근데 이제 카피 테스트 같은 경우는 이 테스트 자체가 랜덤 비트이기 때문에 편하게 그냥 샘플을 뽑을 수 있어요. QA 같은 경우는 지원 길이 같은 걸 처음에 짧은 거 우선으로 풀을 만들어 놓고 이제 샘플에서 쓴다고 하면
네. 그렇군요. So I'm not sure about the NTM that the student mentioned, but so in the sequence kind of learning using LSTM or RNNs, so there are slightly different types of applications where our data items are actually composed of our data set is composed of multiple sequences. So in this case, in the case of maybe machine translations, where each data item is composed of a pair of short English and Spanish sentence, and then it is composed of multiple pairs of these short sentences. But in the case of a character level language models, or not sure if there's any other applications, but sometimes our data set is composed of a single data instance where that instance has really long sequence. Okay, so in the case of learning like a paragraph long kind of character level RNN, and then one paragraph it may be composed of maybe several thousands of characters. So in that case, we just chop them off, right? And then yeah, we learn it using something called a truncated backpropagation through time, right? But yeah, the term is not very important, but we just use like a chopped version in order to form our batch, right? So we have long sequence from 1, 2, 3, 4, and so on. So these are the along the time sequence axis. But then if we set the max length as 10 in our sequence, and then we just chop them off and as the unit of the length of 10, right? And then we form a batch of multiple data instances, right? So I think 이런 거죠. 근데 거기서 뭘 카피해요?
랜덤한 비트를 어떻게 메모리 저장을 카피할 수 있는지.
그럼 이게 그냥 비트 시퀀스예요, 이거가.
네, 그렇죠.
그럼 태스크는 이거를 다 카피해야 되는 거예요?
그렇죠. 그대로 저장하고 있다가 마지막에 이제 알고 그동안 들어온 거를 다시 내려놓고.
처음부터 쭉 레벨 다 기억했다가. 근데 그거를 하여튼 많은 걸 기억을 한 번에 다 못하니까 조금만 기억하는 태스크를. Yeah, very good. Yeah. Okay, so yeah, we can use that kind of strategy in the context of this curriculum learning, and at the same time, in the case of machine translation, where we originally have multiple multiple pairs of these short sentences, in that case, we use something called a bucketing, and that bucketing is like, it's not directly related to curriculum learning, but it's more about computational efficiency and the memory saving and making or accelerating the training process faster. So in that case, in this scenarios, if we form the batch by using the first 3 sequences, and then we will have these 2 input sequences, and then maybe 8 and 3. So when forming it as a single batch, and then we have to store it as a kind of tensor form, which means a multi-dimensional cube, right? Or kind of basically rectangles, or like multi-dimensional rectangles. So we have to pad do the 0 padding with respect to the maximum length available or existing in the current batch. Okay, so in that case, we have to do the computations on these, right? Even though they are filled with a 0, which corresponds to 0 padding, but we have to compute the multiplication, meaningless multiplications over and over, even for these 0 inputs. So we cannot terminate at this point, and this point, and this point. In that case, we cannot do the batch processing or vectorization of our code, right? So in that case, we have to use a for loop, and then at every time step, we have to check the length of the current individual sequence, and then do the for loops only until this this kind of corresponding sequence length. But in that case, using this for loop pays a lot of computational overhead, because the GPU is highly optimized for kind of batch or vectorized processing, right? So in that case, not only just the memory kind of memory is abused, and also the training may be really slow. So one kind of little nice trick to avoid this is to sort them in terms of their lengths, and then form the batch in this sequence, and then there will be less amount of these meaningless kind of 0 paddings, right? Because the lengths will be pretty much the same, right? So this one is called this technique is called a bucketing. So this one is also a frequently used technique in the NLP. So yeah. So I'm not, I didn't do much of a research in the NLP domain. Actually, I haven't done any research on the NLP before becoming a professor until a few years ago. And then because NLP is a one emerging application of deep learning, that's why I started to look at this application. And so I'm not very expert in this domain, but according to some of my students that that spent a lot of time in doing the NLP research, and all these little techniques and all the pre-processing of your data for efficient and proper training, and that's actually almost the main crucial step for doing the NLP research. I mean, running the actual model by running maybe the calling the optimizer and things like that. Constructing the model itself is really, really easy. But the code for doing the pre-processing all these your text data with the variable lengths and also indexing them and then constructing the dictionaries and importing the pre-built word embedding databases and things like that is much more important one. And handling these outer vocabularies too. Okay. Any other comments on this or information to share about this curriculum learning? 이것도 혹시 또 안 사람 없나요? And when attending some major kind of machine learning conferences, including NIPS, and that's actually the only conference that I attended in the machine learning areas. But the frequent application that where I saw this curriculum learning is mostly like robotics or reinforcement learning, right? So when having to learn a certain, that kind of reinforcement learning, I'm not sure how promising it is, but the main characteristic of reinforcement learning is kind of a delayed reward or something like that. So given a long sequence, and then we are given the final output. It's like a many-to-one kind of an architecture. So we don't know which actions across many different time steps, actions that we perform, which one is responsible for a good output or the bad output. So in that case, the model will be difficult to train and so on. So it's kind of a similar problem. So they actually kind of intentionally start with the simple instances or examples when properly training this reinforcement learning kind of applications and models. Okay, and then so what is this scheduled sampling? So when using HELL and then ELLO, so these are, suppose we have to do this character level RNN, like a character level language model, and then these are the ground truths that we have to kind of predict. But at the current epoch, while doing the training, the current output was maybe O, for example. So this one is a predicted output, and this one is ground truth answer. And then we have an option to supply either of these inputs into the next time steps RNN module, right? So with a certain probability, we use either the ground truth and also our actual predicted output, okay? So using it randomly with a certain probability value, and that is called this scheduled sampling. And And the main advantage of doing so, so typically, I mean, what is more standard way of training the neurons? Using the ground truth as an input or the predicted output as an input? Which one is more common? I think using the ground truth information is more common, I think. Because in that case, so I'm not sure if it's related to parallelization or not, but in this case, usually when constructing or forming our the batch input in order to train one iteration of our model, so we usually set our input as D sequence as a kind of many-to-many kind of task formulation, given these input sequence, and then the output should be ELLO. Okay. 그런 것 같아요. 나도 그 차이를 모르겠어요. 아 그래요? 그게 디폴트예요? 뭐가 디폴트인지 아는 사람이 있나요?
원래는 그런 툴스 보통 트레이닝.
그죠. 네. 그게 아마 트레이닝 할 때는, 그러니까 테스트 할 때는 우리가 뭐 당연히 선택의 여지가 없이 프리딕트 된 걸 넣어줘야 되고, 네. 아마 트레이닝 할 때는 정답을 넣어줘야 되는 거예요. 네. 어쨌건, 네. So this kind of default strategy or default way of doing the training is to supply or provide the ground truth information, regardless of whether we predicted correctly or not, right? So the input will always be the ground truth input. I mean ground truth output in the previous time step. Yeah, and when using this one in the place of ground truth input, I mean the benefit of doing so is to make this kind of training scenario more similar to testing, because in our testing we are not provided with the ground truth output from the previous time step, right? So in the testing phase, we have only one option of using the predicted output as an input to the next time step, right? So when using the same or similar strategy, we'll make the training scenario more similar to the testing scenario, and thus I think it seems to be more kind of advantageous, but at the same time it may suffer from kind of slow convergence, at least, I mean, especially in the early stage, because if H was given and then it wrongly generated O, and then the next output is O, and then it has to take into account this input token, but it will be really confusing to generate the L after observing this O as the previous token that we saw, right? So I think if the model is at least behaving properly at a certain level, and then this using this predicted output will make a little bit more sense, but especially in the early stage of training, I think it may slow down the training process, I think. Okay, and I think so scheduled sampling is selecting between these two randomly. I mean, one of these two randomly with a certain probability value. So suppose picking up this probability, this output is 0.7 and this 0.3 and so on, right? So we fix this probability and doing provide this either of these outputs into the input. I mean, as an input to the next time step. But when using this output, I mean predicted output only, and then I think that is called a teacher forcing. Okay, so that is called a teacher forcing. And then why is it called a teacher forcing? We are forcing, or we are enforcing our model to be a teacher. Okay, so in this case, if this one is provided as a ground truth, and then this information was given externally as a correct information, but it has to properly generate L even when this wrong output was given, right? So it is enforcing our model to teach our model by using the wrong, even using the wrong input. I mean, so that's why we call it as a teacher forcing. I think, and then also there is another strategy called a professor forcing. I'm not sure how famous or how widely used it is, but but the name sounds interesting, right? Let me check the citation. Okay, so it's got only like 54 citations, so it may not be used widely. But anyways, I mean, I tried to study or look at this paper before our class, but I didn't find time, so I cannot explain it. But if anyone knows how it works, and then feel free to share. 이거 어떻게 동작하는지 아나요? Professor forcing. 네, 뭐 기회 되면 한번 읽어보고 나도 혹시 알게 되면 공유를 해줄게요. Okay, so let's take some break for 10 minutes and then resume at 3:30. Okay.
하셨잖아요. 근데 포켓팅 하면 매번 텐서 사이즈가 달라지는 거예요? 배치마다?
네.
그렇게 해도 되는 거예요?
네. 그러니까 배치는 그때 이제 구성을 해서 하여튼 서로 다른 이터레이션에서 구성되는 배치 사이즈는 달라. 그러니까 이터레이션은 기본적으로 포룹이 있잖아요. 그러니까 포룹에서 우리가 매번 뭔가 서로 다른 행동을 할 수가 있는데 벡터라이즈된 코드는 이제 한 방에 뭔가 내부적으로 다 하드웨어 가속화된 걸로 해야 됩니다.
Can we meet for a short?
Yeah, I think so.
이해가 안 가는 게 하나니 그 RNN에서 그 다음 그 RNN 모듈들이 이렇게 있다고 했을 때
네.
이전 스테이트에서 뽑은 아웃 프레딕션 값을 인풋으로 넣는 게 아니라 그라운드 트루스를 트레이닝 단계에서 넣는다고 했잖아요. 그럼 거기서 티처 푸싱이라는 건 뭐예요?
그러니까 티처 포싱은 그 트레이닝 단에서 이제 입력값이 그러니까 그 전에 제대로 뭔가 생성이 H 다음에 H가 들어갔을 때 E가 생성이 됐다라고 가정을 하고 이 네, 과거에 이제 그 생성됐을 그 맞는 그 코렉트 인풋 아웃풋을 여기 인풋을 넣어주는 게 이게 일반적인 트레이닝에서 아레나 트레이닝을 할 때 매니투매니에서의 과정인데
그런 트루스를 넣어준다는 거죠.
그라운드 트루스를 넣어주는 게 일반적인 건데
네.
그라운드 트루스가 아니라 얘가 생성한 거를 이쪽으로 넣어주는.
근데 그렇게 하는 이유가 뭐예요? 그러면?
그렇게 하는 이유는 이게 여기 좋은 질문인데 이게 H 다음 H 다음에 이제 O가 이렇게 나오면 어떻게 보면은 O가 이렇게 한 번 잘못 나왔어요. 그러면 이제 중간에 한 번 잘못 나오면 그 뒤는 다 스크롤업 된다는 말이죠. 그러니까 다 어그러지는 거잖아요. 그러니까 무슨 소리냐면 H 다음에 O가 나왔으면은 여기에 L이 나오기를 기대하는 거는 거의 불가능할 수 있는 거예요. 근데 이제 O가 들어갔음에도 불구하고 L이 나오도록 하려면 얘가 그러니까 뭐 예를 들면 E라는 그러니까 맞는 아웃풋을 생성을 했을 때뿐만 아니라 이런 뭐 좀 헷갈려서 O라는 어떤 잘못된 아웃풋을 생성을 했어요. 그 잘못된 아웃풋이 이 다음 스텝의 인풋으로 들어갔을 때조차 중간에 한번 이렇게 교정이 이렇게 가능한 어떤 이런 교정할 수 있는 능력을 부여를 해주도록 하는 거예요. 그러니까 트레이닝을 그냥 저기 그라운드 트루스만 넣어주면 이건 어떻게 보면 좀 약간 온실 속의 화초를 키우는 거죠. 그러니까 그 전까지의 인풋이 그 전까지의 시퀀스가 완벽하게 다 맞아 떨어졌을 때만 그 다음 거를 이렇게 또 잘 생성하는 그런 식으로 모델링을 지금 학습을 시키는 건데 실제로는 중간에 하나가 삐끗해서 틀렸으면 그 다음부터는 그러면은 뭐 그냥 볼 것도 없이 다 틀리도록 모델이 그렇게 하도록 둘 거냐 아니면 중간에 하나쯤 틀렸을 때도 이제 뭔가 다시 고칠 수 있는 능력을 좀 부여를 해줄 수 있도록 할 거냐 그런 게 이게 티처 포싱.
글로벌을 아웃풋을 쏘는 게 어떻게 방법도 내가 알려준 것들 진짜 맛있겠다. 진짜 대놓고 야 이러는 게 아니야. 야 진짜 맛있겠다.
형이 더 떨어진다. 가져와 봐라. 내 입 앞으로 가져와 봐라.
저 빨간색 3개가 된 거야.
어떤 학생은 자기 학번조차 잘못 썼던데요.
아니네. 나는 다 맞아. 처음에 D가 뭐였지?
학번도 틀리고 퀴즈도 다 틀리고.
이번 나빠라.
Okay, let's continue. So yeah, again, if you have any questions, yeah, feel free to let me know. Yeah.
이제 그 아래에서는 배치노멀
진호요? 그러게요. 쓰지 않았어요.
그것도 수직으로
모르겠나? 아는 사람. Does anyone know how we use or whether we use batch normalization in the RNN? I'm not sure. Maybe, yeah. Maybe we can use the batch normalization. Yeah, I have no idea. Maybe I'll ask some of my students that does this NLP stuff. Yeah. I mean, the tricky part when applying the batch normalization in the RNN is that, I mean, yeah, it may be wrong. I mean, yeah, so in this case, so batch norm should be recurrent, right? So batch norm would be applied to the output of the just before the hidden state vector. Yeah, I don't even know where to apply the batch norm in the LSTM structure. Yeah, but the tricky part is that if we added the batch normalization layer, and then that batch normalization should be also recurrent, which means that the batch normalization parameters should be the same across different time steps, right? Because it doesn't make sense to use a different parameter sets on different time steps. Yeah, for the batch normalizations. So that may not. I mean, that may not make sense to apply this batch norm. I mean, yeah, I have no idea, but maybe later, yeah, I'll see if I can get a better answer. Any other questions? That was a very good question.
아래에서 쓰긴 쓴다고 있거든요.
아,
그래도 있는데
네. 보통은 안 써요, 그러면?
라이브러리는 잘안 되는 있긴 있는데 레이어문까지 이제 가면서
아,
그냥 배치문이랑 레이어문
그러니까 배치놈을 집어넣으려면 뭔가 LSTM 셀 내부적으로 집어넣어야 된다, 이거죠?
히든 스테이트에만 이제
네.
배치문을 그래서 히든 투 히든으로 바로 쓰더라고요.
그러니까 여기서 히든을 이쪽으로 올릴 때?
아니 히든 투 히든으로.
여기서 이쪽으로 갈 때요?
네.
아, 근데 이게 지금 이렇게 돼요. 여기가 탄 H로 되니까 이게 마이너스 1에서 1 사이고 히든 스테이트 벡터들은 다 마이너스 1에서 1 사이잖아요. LSTM이든 뭐든 탄 H에다가 이제 아웃풋 게이트를 거치니까 그 다음에 얘를 리니어 컨비네이션, 그러니까 뭐 이런 벡터가 뭐 이렇게 있겠죠. 마이너스 0.7, 0.5, 0.2 여기에 이제 리니어 컨비네이션이 붙어서, 그러니까 이 HT-1이고 이게 WHH인데 WHT-1에서 HT로 가는 그 트랜스포메이션이고, 그 다음엔 그 다음에 어디다 써요? 여기다 써요? 요거에다가? 보통 난리니어 유닛 직전에 넣어주잖아요, 배치노.
아예 히든 스테이트 확정되고 이제
네.
아웃데이트까지 거치고 나서 히든 스테이트에다가 적용하는 거.
리니어 레이어 전에?
네, 그냥
리니어 레이어 전에?
네, 여기는 LSTM을 쓰긴 했는데.
아, 그러니까 LSTM 다음에 넣을 때요?
네.
그러면 LSTM에서 이걸 리니어 트랜스포메이션 하니까 그렇군요. 하여튼 LSTM의 바깥쪽에다가 건다.
안쪽에도 하는 버전이 있는데
근데 잘은 안 쓴다니까요. 보통 쓰나요? 쓰는 경우가
쓰는 리포트를 본 적은 별로 없어서.
거의 아래는 LSTM 계열에서는 안 쓴다. 배치노는. 네, 뭐 성급한 결론일 수도 있지만. So yeah, in the case of fully connected layers or convolutional neural nets, when do we apply the batch norm? It is just before. Let's see. Where's batch norm? Okay. Give me 1 second. Okay. Yeah. So the point where we add a batch norm, I mean, although batch norm is optional, although we use it frequently, at least in the fully connected layers or this convolutional neural nets, and then we usually perform the linear layers. Okay, and then when giving it as an input to the nonlinear units, such as a 10H or maybe ReLU and sigmoid, and then if the output the ranges of the output from this linear transformation is quite deviating from 0. So, for example, if the ranges of the linear transformation output is all maybe around here, which is far from 0, and then our sigmoid and the 10H will actually have a saturated output which kills the gradient, right? So usually the point where we add a batch norm is just before this nonlinear unit. Okay, so it is also the same as the convolutional neural net as well, because the convolution itself is also a linear transformation. So before applying the ReLU, we typically do the batch norm, in between. I mean between the conv and ReLU nonlinear unit. Okay. So in the case of ReLU, ReLU looks like this, right? So in this case, the gradient will be killed completely, or it will be just preserved also completely. But in this case, still the same problem persists, or this kind of ranges of our general outputs. If that output is around here, and then we don't actually add any kind of non-linearities, right? So this ReLU has no effect when having the output ranges from the convolutional layers are all kind of quite like large positive values. Or if we have this signal ranges, and then it will kill all the signals completely. So we need to also adjust our the range of our output signals from the conv layer around 0. So that's why we use the batch norm, between the just before the nonlinear unit. 컴브 이렇게 쓰는 거 맞죠? 그죠? 배치놈 여기 쓰죠? 렐로 직전.
그러면은 그런 액티베이션 성상 생각 안 하고
네.
인풋 피처에서 그런 디멘션만의 값의 범위가 다를 때 그런 걸 그냥 단순히 조정해 주기 위해서 그런 배치는 어떻게 하나요?
그러니까 이 배치놈은 다 디멘전별로 이렇게 다 적용이 되기 때문에 지금 이야기는 이게 fully connected layer가 이렇게 노드 3개로 빠졌다, 뭐 4개에서 3개로 빠졌다. 그럼 이 3개 각각의, 그러니까 말 그대로 배치별로 노멀라이제이션 하기 때문에 이제 배치 사이즈가 100이다. 그러면 노드에 걸리는 혹은 저 노드에 해당하는 100개의 어떤 스칼라 값이 있는 거고, 그죠? 두 번째 노드, 세 번째 노드 이렇게 있고 각각 따로따로 이렇게 배치놈을 적용을 해주거든요. 노드. 그러니까 물론 뭐 셋 다 배치놈 적용하거나 아니면 말거나인데 기본적으로 배치놈에 해당하는 파라미터는 각 이 노드별로 혹은 디멘전별로 존재하죠. 네.
그 아예 그런 레이어 거치기 전에
네.
요구하는 인풋에서
네.
그런 예를 들면 그 띵에 따라 그
네.
밸류의 원래 지금
네.
편집이 다를 수 있고
네네네.
그런 걸 단순히 조정하기 위해서 넣는
네. 보통 아마 할 거예요. 네. 이게 그러니까 이게 하여튼 모든 그러니까 이게 뭐 키, 몸무게, 혈액형. So it is a height and weight and things like that, which has all the different distribution. So in that case, I think yeah, it is not called a batch norm because batch norm has the trainable component, right? So if it needs, so this is typical or original kind of normalization process that was done in the first phase of the batch norm, and then the second phase is actually letting or allowing our model to shift and scale the input signal in their own manner, right? So these two parameters are kind of adjusting the mean and the variance as not as a 0 or 1, right? So yeah, but I think in the case of an input, I mean, when normalizing input dimensions or input features, I think just the standard normalization is applied for each of our input dimensions. So if we have 100 people's feature vector of a height, weight, and so on, and then for 100 values of one height, we make it as having a 0 mean and the unit variance or the variance of 1, right? I think we will do this kind of processing. I mean, that actually makes it sense. I mean, that actually make our He or Xavier initialization actually works and makes sense, right? Because in that case, suppose we have an output node 1 here, and then the fan-in has the 3 kind of input nodes, which all has the 0 mean and the unit variance. And so if we initialize those weight as having also unit, the 0 mean and the maybe 1/3 of a variance, and then we can still make the output value as having 0 mean and also unit variance. Okay, but this kind of initialization strategy will not work if those values are not properly normalized, so that they become 네, 아마 이건 디폴트로 하는 것 같은데요. And also we also do this kind of thing for the image data as well. So given a 2D kind of images, right? So there are slightly different input normalization technique. I'm not talking about the batch normalization, but just the input kind of normalization, so that each pixel value. So suppose we have so it's like a 64, 640, and 480, and maybe the channel 3 channels we have, right? And then we have 100 pictures or photos, and then we will have 100 values corresponding to this right bottom kind of position, right? And then I mean, in that case, we can kind of do the normalization separately in the different pixel positions, but that doesn't make sense, right? So that doesn't make sense. So we can either compute the global mean of all these RGB values. So suppose we have a maybe 10 and 20 as a pixel, photo or picture size, and then in total we have 200 and then 3 channels, and in total we have 600 pixel values in one photo. And then if we have maybe 15 different photos, and then we multiply them, and then 9,000 pixels, and then we compute the mean, and then compute the variance, and then we can apply this normalization on every pixel like that. But also we can do the this kind of normalization like a channel wise. So within the red channel or green and the blue channel, we can do this kind of normalization separately. I think that yeah, channel-wise normalization is the most common kind of practice that we do. 네, 그러니까 R 따로 뭐 이렇게. 네. Okay, so so back to this batch normalization issue. So what I thought of as a kind of a little bit weird was, so suppose we have this HT as ranging from -1 to 1, and then typically the point where we apply the batch norm is just before the nonlinear kind of units, and after, and also after the linear transformation. But these signals will all be first transformed linearly, I mean through the linear transformation, right? In order to generate like yeah, forget gate, input gate, and so on. So they will all first be transformed with the linear transformation, and then be applied with the sigmoid or the 10H. So I thought like the proper way of doing the batch norm is just before or after this linear transformation, but yeah, the student said that this one is first, yeah, batch norm is first applied before the linear transformation. But I'm not sure how much it makes sense. And okay, any other questions so far? Okay, and then the blue score. Blue score. So the blue score, so it's basically a geometric mean of the precisions of unigram precision and the bigram precision and the trigram precision and so on. Okay, and then the precision also has, it's like an accuracy measure ranging from 0 to 1, right? And so the unigram precision, suppose unigram precision was like 0.8 and the bigram precision was 0.7 and 0.6 and maybe 0.75. So this is unigram, bi, tri, and 4gram. And then we can do this average, take the average of these 4 numbers, but we do the geometric mean when doing the average. Okay, so that is also the one kind of important aspect of this blue score, which penalizes the lowest value a little bit more, because the mean value of these 4 numbers when taking the geometric mean will be biased towards the lowest value, right? So yeah, and then also just like the weighted average in terms of arithmetic mean. So when doing the average, so we have, suppose we have 2 numbers, and then the typical average will be 4, right? But we can think of the weighted average. For example, weight will be something like this, and then this one will be just an average value, or weighted average, right? Which takes into account this first value with the 40% and the second value as a 60%, right? So similar to this, we can do the weighted average on the geometric mean, right? So geometric mean is something like this. So 3 to the power of 1/2 and 5 to the power of 1/2. So these 2 numbers should sum up to 1. But if this value was 0.4 and 0.6, and then this can be viewed as a geometric average. I mean, weighted average of this geometric mean, right? So this one is taking this value more into account, right? So we do the same thing on this blue metric. So if we have 4 different precision values from unigram, bigram, and so on, and then if we think that bi and the trigram, I mean, in the just the geometric mean with the equal weight, and then what will be the weight? It will be 1/4, right? So that will be the geometric mean of these 4 numbers, but with the using the equal weight. But if we think this this value is more important, and then we can increase this weight of this value as maybe 0.3, and then we adjust the other values in terms of these weights used in the geometric average. Okay. then yeah, and then in that sense, I don't think it makes sense. I mean, I don't think it's a correct geometric average, weighted average. So these are ways associated with the precision value with the unigram and the bigram and so on, but they are not summing up to 1. So I think it's kind of weird. But yeah, but if we use this as, I mean, this, if we use this consistently for all the methods that we compare, and then the relative average will be, I mean, yeah, their relative order will not change, right? So it can be viewed, yeah. It seems like a little bit of a generalized version, but at least you got the idea where we think the unigram precision as more important one, and the bigram as a less important and less and less. Okay, so that is the meaning of these weights. And then when computing the precision for unigram, bigram, and so on, so how do you compute the precision? So in that case, so precision, yeah, we actually determine whether each of the predicted or generated tokens in the predicted output, I mean, we consider whether each predicted token is included in the ground truth sequence, right? So if it is included in the reference, and then it is considered as a correct output, okay? And American is not here, so it is counted as 0. And so we basically compute the average or the mean value of these either 1 or 0. But here, so there is a kind of one additional trick that we used in the blue score. So like in the example of and if we have a many and maybe 3, I found 4. Are there any? Maybe that's all. Yeah. And then if we have only 4 in the ground truth, and then we only treat or consider only 4 of them out of 5 generated token are correct. Okay. So in that case, it is considered as correct one, but it's incorrect one. So we assign 0 value on this guy. Okay. So that way we can avoid like the model to repeatedly generate the same tokens meaninglessly. And then in the case of a bigram precision, okay. So bigram precision, so we consider these bigram of generated token sequence, right? And then determine whether this token is existing in the ground truth bigram tokens, right? And that's how we compute the precision of the bigram, bigram precision. Okay, and then this thing, gravity penalty, is associated with the penalization imposed to the excessively shorter sequence, right? So the main blind point of this using precision is that if we use really highly confident, the short sequence of a really high confidence tokens, and then those 3 tokens will be likely included in the ground truth, right? So in that case, we might be able, it might be more, easier to achieve a much higher precision value, right? But if we use more and more, if we generate more and more tokens, and then given the limited number of tokens available in the ground truth, okay, so in that case, we may, our precision may be lower than the one with the shorter sequence. So in order to penalize this situation, we assign this kind of a weight, and that weight is defined by this. Okay, so if it generated, if it generated a longer sequence than the ground truth one, this ground truth one and this one is a longer sequence, and then it will be greater than 1, right? And then it will be negative value. So again, this one is the case where our machine translation is longer than the ground truth, right? So in that case, the minimum value is negative value, and then exponent negative value will have some weights less than 1. Oh, sorry, yeah, I was thinking opposite or wrongly. So if our machine translation result has a sequence of 5, but the reference or ground truth had a 4, and then this one will be positive value, and thus minimum between 0 and this positive value will generate the positive value. Okay, and then we will boost up this precision values. I mean, as like more than 1, right? So I actually haven't thought about the actual cases, but I think you guys get the idea of like giving more penalty or down weight the precisions generated by the really short sequence, and giving more boost or the performance increase when we generated a really long sequence. Okay. 네. 요거요? 요거? 네. 해준다고 나와 있는데요.
그러면은 저희 로그 블루에는 그냥 좀 빠져야 하는 거예요.
아, 이 밑에요. EXP가 그러네요. 맞나요? 뭔가 이상한데? 로그의 EXP. 헷갈리네요. 이거 뭐, 이게 EXP? 이거 맞아요? But anyways, yeah. Maybe there might be wrong. Something wrong. 근데 이거는 어디서 나온 거예요? 이 EXP는? 네? 그래요? 그러네요. 그러네요. 그러면은 이것도 이 안에 들어가는 게 대충 맞나? 아니, 상대적으로는. 또 맥스가 아니라 또 미니에요.
저 미니 맥스로 바꾸면서 마이너스.
네. 뭐 그런 것 같아요. 네, 뭐. 근데 기본적으로 이게 하여튼 얘가 있어도 좀 헷갈리는데 얘가 없어야 되는 것 같죠? 일단은. 하여튼 쟤 때문에 뭔가 머릿속이 혼란스러운데. 나중에 뭐 아이디어는 알겠죠? Okay, so yeah, this one is a kind of blue score, and so the main idea, I mean, yeah, you get the idea roughly, I think, and yeah, just to point out some specific example. So Chris Manning mentioned like last night I ate, for example, ramen. Okay, so in this case, this one can be placed over here. So suppose this one is our ground truth, and then this guy is generated at the end of our generated sequence, right? So in that case, the entire sequence may not match, right? But in that case, at least we can expect like a full precision or the perfect 100 precision in terms of a unigram, and also relatively high accuracy or high precision value for bigram. But in the case of trigrams, yeah, it may be kind of wrong, right? Because ramen last night will be considered as a kind of valid ground truth token that we have to generate, but that token is not available in our generated sequence. So that way, yeah. But what's the disadvantage of using only the unigram one? In the case of unigram one, 8 I ramen night last. So in this case, it will generate the perfect 100% precision for the unigram case. But in that case, it doesn't consider any kind of sequence information. Okay, so considering all these partial sequences, that is called this blue score. I didn't understand this figure, but at the end of this slide, Chris Manning mentioned that we usually use only one reference translation. So although there may be many available or many different ground truth translation of the same source sentence, but we use only one of them. Okay, and then using it, we evaluate or compute this blue metric. Then about this figure, can anyone explain this figure? I tried, but I couldn't understand this at all. 이거 아는 사람 있어요 혹시?
어떤 번역 문장에 대한 에리커스나 플루언시에 대한 코릴레이션이 굉장히 잘 존재한다. 휴먼 자체만 블루 스코어가 아니라 코릴레이션. 휴먼이 좋다고 했을 때도
네.
블루가 좋았고 또.
네. 그러면 요 초록색과 요 빨간색은 이게 그러니까 각 항목에 대해서 휴먼이 저지를 어떤 한 문장에 대해서 이렇게 했다는 거죠.
네.
그러네요. 네. So I was confused because we have to think about these two different measures simultaneously. But the question would be like those values corresponding to this human judgment would be like by using this Likert scale. Somewhere there was a kind of a Likert scale kind of thing. But anyways, so our questionnaire to give to our users or participants in our user study will be to given the source and the generated sequence or the target sentence, they evaluate or assign the score, the adequacy and the fluency or kind of a naturalness of the generated sentence as the score ranging from maybe 1 through 7. Okay, so 7 meaning that it's highly adequate or like fluent. And then for a particular sentence, one sentence will have these 2 scores assigned by the human, and then their kind of blue score, which is shown to be a variant of this blue score, and okay. So those 2 are pairs. I mean, those 2 are corresponding to the same one because they have the same blue score value, and maybe these 2 and these 2 are the same actually, and then we can compute this R squares or this correlation coefficient between these 2, and then okay, then so there are many different evaluation metrics in order to automatically compute the performance of the quality of the generated sentence outputs in the machine translation application. And then I have no idea about what these are, but the only thing that I know about this meteor is that in that case it is actually using, does anyone know the difference or the main characteristic of this meteor measure in comparison to like blue score. 이건가 아니면 뭐 이런 것도 있는데. Cider. I'm not sure which one has the aspect in my mind. But. So one disadvantage of this blue score is that so they don't count any kind of similar words at all, right? So maybe I'm not sure. Both received, instead of using received, suppose we generated maybe got, okay? So these two words can be shown, considered as a similar word. But in this case, it is still assigned a 0 score at all, right? No score at all. So we can kind of think of, the word similarities between this and the matching kind of word found in our ground truth, right? So in that sense, how can we obtain the similarity between a particular pair of words? We use word embedding, right? So given the word embedding vectors, we kind of compute the most similar words available in our ground truth tokens, and then and then assign the score on this word got as some positive value instead of just complete 0 scores. Okay, so such a measure incorporating this word similarity instead of just exact match or not is corresponding to, I'm not sure which one is corresponding to these two, or maybe both, but those other measures are taking into account those kind of word similarities as well. Okay, then so the making the softmax computation more efficient. There are several ways, although I'm not very familiar with them. But this hierarchical model seems to use kind of a hierarchical softmax that we discussed when studying the word2vec, right? So in that case, so if we have maybe a vocabulary size of 1024, and then we have to compute the 1024 different inner products. But when using the hierarchical softmax, we are using only these number of inner products, right? So that, maybe, So somehow these kind of hierarchical structures of these all the available tokens, right? And then tracing to the most probable words, starting from the root node, is corresponding to this hierarchical model. And then this noise contrastive estimation. So this one is, I found this technique, taught in one of the online lectures that I studied. But in my understanding, that is actually the same as the negative sampling. Okay? So the negative sampling, all the negative keywords. Okay, unlike the ground truth keywords, in the context of word2vec. Okay, so I study mass, and then given the study, we should observe mass, not the other words. So all the other words that are not observed are considered as a noise. Okay, and then we actually suppress this kind of probability of observing these noise words, and that is corresponding to this noise contrastive kind of estimation. But this method is based on some kind of probabilistic kind of context or literature. And have you guys studied one of the oldest neural net models called the RBM, restricted Boltzmann machine? So that has really nice theories and backgrounds. Mathematical backgrounds, and also it seems like it's having some kind of background in the physics literature as well. But anyways, so that is a kind of oldest version of our neural net that Jeff Hinton has really focused on until maybe 10 years ago or so. And then this model is based on the probabilistic kind of kind of maximum likelihood and the EM thing and so on. And so in this RBM thing is basically kind of it can be kind of viewed as a kind of auto encoder. Okay, auto encoder. So in the case of an auto encoder, unlike the binary classification or like a classification with the small number of classes available, in the case of an auto encoder, if we have a maybe 10,000 tokens, I mean 10,000 vocabulary size, and then output should also be the 10,000, right? Because we are considering the auto encoder structure. So in that case, we kind of also want to avoid all the computations corresponding to the each of our output nodes. So in that literature, they used this noise contrastive estimation kind of thing. And then I forgot the name of that guy that did the lecture, and I kind of like that lecture. I'm not sure if he's still actively doing the research, but 그 사람 누구죠? 누군지 혹시 아는 사람? 휴고 라로시아? 네, 라로셀인지 라로쉘인지. 네. 네. So yeah, Hugo Larocel or Shell. Yeah, he's I think he's a family in he's a kind of part of this big family or kind of mafia kind of thing from I think Yoshua Bengio. Yeah, but anyways, he's a kind of early pioneer in this deep learning. I mean, in the early age, and then he has some online lectures about this deep learning, especially like including these early models, such as this RBMs and things like that. And so, yeah, I think his lecture was quite good. Although I'm not sure if I finished it completely, but there is a lecture about this noise contrastive estimation. So if you're interested, and then you can look at it. And this one is, So in the case of this noise contrastive estimation or the negative sampling, so Chris Manning said it's not GPU friendly, but I'm not actually sure why it is not GPU friendly. Does anyone know? So in the case of on word-to-back, we will have a maybe suppose we have 100 pairs of an input and output words that forms our one batch. Okay, so in that case, all these are positive examples, and then in this kind of negative sampling and things like that, we have to generate some k number of negative samples associated with each positive input-output pairs for each of these 100 pairs, right? And then and the reason why this is not GPU friendly is because we have to generate these negative samples on the fly. So in that case, we cannot do the batch processing or parallelization done internally within the GPU. So that's kind of my guess. I mean, that's kind of my understanding from what Chris Manning said, but I'm not sure. But because we can pre-obtain or pre-compute all these negative samples in advance when doing this batch processing of literally our one batch. So I'm not sure why it is not GPU friendly. 네. 하여튼 그 배치 이터레이션은 포룹으로 도는 거고, 그다음에 각 포룹의 맨 처음에 네거티브 샘플링을 각 그 배치에서 하나하나의 포지티브 케이스들마다 뭐 3개씩 네거티브 샘플을 생성해야 된다 그러면 뭐 총 300개의 네거티브 샘플을 다 랜덤하게 생성을 해두면 패러렐라이제이션이 가능할 것 같습니다. 그거를 가지고 보스 포지티브 앤드 네거티브 배치를 총 400개가 되겠죠. 400개 인풋 아웃풋 페어. 그렇게 해서 뭐 포지티브 레이블 1 주고 네거티브 레이블 0 줘갖고 학습을 하면 될 것 같은데 왜 그게 GPU 프렌들리가 아닌지 잘 모르겠어요. 뭔가 하나하나 예제들마다 그때그때 뭔가 네거티브 샘플을 생성을 해야 된다라 그러면 그 패러렐라이제이션이 안 되니까, 즉 배치 프로세싱이 안 되니까. 근데 네. Okay, well I don't think it's that much important. Let's see. Okay, so I'm not sure if these slides were included in the lectures or presented in the lecture video, but I found these lecture slides, just now. But let me just briefly introduce what the Sentinel is. Okay, Sentinel is. So in the case of maybe a study mass. And then in the decoding phase, so yeah, Korean is the only language that I know other than the English, so I have no option. Okay. So in this case, in the case of an attention model, so attention vector, the attention weight should be is always the output of the softmax. So it will always be sum to 1 vectors. So it means that we have to attend, or we have to assign some weights to the existing words, right? So that their total sum of these attention is always 1, right? But what if we don't want to attend to any of these input sequence? Okay, so in that case, for example, maybe let's think about the opposite case, and then maybe 나는 학교에, and then it will when generating this I, and then we will attend to this one, and then when go, and then we will attend to this one, and in the case of 2, and then it is like it should be generated. I mean, when thinking about the RNN model at this point, when generating this keyword token, and then the previous output token will be an input token here, and then the previous hidden state vector will be given, and also in our RNN module we will have a context vector, which is a weighted average of these encoding vectors associated with this 나는 학교에 간다, right? Okay, and then the weight vector will be like maybe 2, 0.3, and 0.5, for example. Okay, but in the case, when generating these 2, and then in this situation, we have to rely only on, or mostly on, the pure language model. I mean, pure English language model, not just based on the input sequence, right, in Korean. So in that case, we don't want to attend to any of these input tokens. So in that case, we want to assign really small attention weights. Okay, so in that case, we violate the constraint so that the softmax vector to sum up to 1, right? So in that case, we kind of reserve additional vector as a kind of a dummy dummy encoding tokens. Okay, so in that case, it is all 0 vector, just like a padding kind of thing. And then we assign a really high attention to it. Okay, so maybe 0.95, 0.96, and in that case, we can give no information at all from the input tokens, so that the model don't get confused by these input tokens, and then focus on this pure English language models, so that it can generate this too, purely based on this goal. Okay. So this kind of thing is called a Sentinel. Okay, and this kind of Sentinel, this one is kind of explicit version of this Sentinel thing, but I think this show, attend, and tell, which is kind of the original attention model paper, also had a kind of this kind of aspect. In that case, they had a kind of a sequential kind of modeling, or they modeled, or they implemented this idea kind of sequentially. So in this case, we had another dummy encoding vector, right? But in the original show, attend, and tell papers, so we still have the sum to 1 vector. So it will attend to some vectors non-trivially. And then given this vector, and then we also have some kind of gating layer here, okay? And that gating layer is generating the output, I mean scalar output ranging from 0 to 1 from the sigmoid output, and then it will, it will kind of shrink down the context vector, okay? So yeah, but anyways, this Sentinel kind of thing was, I think, first proposed in the Richard Socher's papers. In the application of a image caption, and then they showed a better performance than the previous show attendant kind of paper performances. But anyways, this is the notion of the Sentinel. So you can maybe add this kind of aspect. I think it's quite easy to add into the existing attention model. And then also this kind of copy and pointer network. I'm not sure if it was explained at all in our lecture, but let me just briefly explain what this means. So, so there is a model called a CopyNet. Yeah, I don't like the name because the name sounds a little trivial, but there is a model called a CopyNet, and this paper, I mean the performance improvement is really marginal. So when you even when you don't use this CopyNet, the performance may or may not be better than this advanced model of CopyNet. But in this CopyNet, the main intent or motivation was to be able to handle the out of vocabulary kind of tokens. So like in the case of a chatbots or question answering kind of scenario, maybe, hi, I am John, and then suppose, given these input sequences, suppose we want to have the output as hi John. Maybe that's it. And then suppose this John, because that's the unique person name that we didn't see in our training example. And then this one will be considered as a kind of onc token, right? And then, and then in that case, also because this word was not registered in our vocabulary, it's just an onc word, right? I mean, unknown token. And thus, we cannot, I mean, there is no way to generate this token of this, I mean, these unseen tokens, right? But still, this unseen token was actually seen in the input sequence, right? So the main intent of this CopyNet is to allow the model, I mean, whenever needed, I mean, only when the need is there, the model should be able to copy, even for some unknown tokens, into the decoding sequences. Okay. So in this case, we kind of have like two different softmax probabilities, okay, and then we somehow add them together using some weights, okay, by using some gating layer and so on. And then the first one is the typical kind of softmax across our vocabulary. So if we have 100 keywords registered in our vocabulary as a unique keyword, and then this one will have the softmax vector that has the dimension of the 100, like this, right? The distribution over 100 different keywords. And then also we think of like the distribution, okay? The softmax distribution across the input sequence, okay? So since we have 4 different keywords as an input sequence, and then we can construct the 4 different softmax vector across this input sequence. Okay, and then in this case, hi and I am. So those 3 keywords would be likely just already registered keyword that are found in our vocabulary, right? Only this John is unseen keyword. So some will be already seen or already registered keyword, but some other will be unseen ones, right? So we kind of add these two distribution vector together with some certain weight, and so yeah, like so this one is sum to one vector across the 100 different keywords, and then this one is sum to one vector across our input tokens, and then suppose we decided from our gating module, we decided to combine these two probability distribution with these weights, okay? And then suppose this I has the probability of 0.2, and then this 0.2 times 0.7, which is 0.14, this probability will be added to maybe, so this one is I, okay? So I had the probability from just the typical softmax as maybe 0.5, for example, and then this guy and this guy is multiplied, and then this guy, this 0.14 will be further added to that probability, okay? And then what about this John keyword? So in that case, we actually concatenate them, or those unseen keyword through these 100 dimensional vectors. So this one has the length of 100, and in the 100 first place, we just temporarily registered this kind of John keyword. Okay. Okay, and then finally, we pick up the argmax token from this, and so at least, although the model should have a proper decision, should make a proper decision, but at least the model should be able to generate the unseen tokens which was first seen in the input sequence. Okay, so that is the main idea of this copynet. Okay, so in this case, so I still remember that I was really confused, and I somehow I was a little frustrated that I have really such a shallow kind of insight or background when studying this copynet, because so when doing the softmax vector, we typically use a fixed length of a vector. So if we have 100 different keywords registered in our vocabulary, and then we always generate 100-dimensional outputs as our softmax layer, right? But in this case, so we have the we should generate the softmax vector across the variable lengths of an input sequence. So sometimes our input sequence will have 4 different input tokens, but sometimes our input token will be maybe I am happy John, something like that. That is the 4, but that can have a different length, and also each different dimensions, or each dimension, I mean each word corresponding to each position will have a different meaning, right? Unlike the predefined 100-dimensional softmax vector. So in the case of softmax vector across predefined categories, and then the first dimension will always be fixed as a particular keyword, right? So I was not sure how it is even implemented and so on, right? But I found that, I realized that this softmax vector over our input tokens are just nothing but our attention model, right? So this is really an attention, right? Does it make sense? And how does attention model deal with these variable lengths of an input, and also different meanings associated with the different dimensions at a time? So for example, the first dimension was what was that? Oh, okay. High is corresponding to the first dimension, but in the next input sequence, and then maybe that keyword will start with I, and then the first dimension will have a different meaning, right? So it doesn't make sense to use the just typical softmax layer. So the meaning of each dimension is different across different input sequence, and also the lengths of our categories are also different. So how does the attention model deal with this kind of problem? attention에서 이거 어떻게 하죠? So this is really a attention vector, right? Across the input sequence, right? And then what is the typical way of implementing attention that can handle this variable length of an input sequence? and different meanings. So I'm not sure how meaningful it is, but at least to me, yeah, I felt it is a little bit interesting to see the difference. But let's see. So let me see if I can find. So when doing the image, the classification task, and then the first category is determined as maybe fixed as cat, and then the second dimension is fixed as maybe dog and so on. Yeah, okay, this figure. Okay. Okay, so suppose we are given 4 different pixels composing our image, and then suppose we think of just a single layer softmax kind of a multi-class classification. Okay, so we are performing this linear transformation so that we can generate a 3-dimensional vector and then perform the softmax on that, right? And then from here, these are the input signal, input feature vector, and then you can understand or view this each row as a kind of template, okay, template vector that we want to look at. In order to generate the score, I mean likelihood score of the cat and dog and maybe sheep, okay, and we can even like visualize this kind of thing. Maybe as this one, right? So yeah, it says the lecture from CS231N, and so this one, okay, so this one is actually the visualization of this template vector corresponding to this row, okay, that generates the score of the cat, right? And so if this dimension is fixed as a cat, and then also correspondingly this template vector that we use to look at the pattern of the cat or likelihood of a cat is also fixed, and then they will be it will be used to compute the inner product with the input vector, and then we generate. We can just ignore the bias, and then we can generate this likelihood score of being cat, right? But here, we now have a different meanings for the first dimension, right? So it's sometimes I, and sometimes it's a high, and so on, right? And then the lengths may be different. So we cannot even construct this fully connected layer that has the fixed matrix size, right? So in that case, how we handle it is in the attention model, by considering really the simplest model based on the inner product one. So what is this one? What is this one? This one is corresponding to so suppose we are given these encoding vectors for these input or source sentence, and then this vector is actually working as this template vector corresponding to the cat. Okay, and then what is this one? This one is the hidden state vector in our decoder, right? And we are comparing that decoding the hidden state vector from the decoder at a particular time step as the input vector, and then we kind of match by doing this inner product with these things. So now those vectors can change depending on our input sequence, and also it can it can have a variable length, right? So that's how we compute this kind of a softmax kind of thing. Given this varying meaning of each dimensions and the varying lengths of these softmax vectors. Does it sound interesting or not? 네, 하여튼 뭐 그래서 하여튼 뭐 아까도 얘기했듯이 좀 이거를 저런 소프트맥스를 어떻게 구하나. 네, 그래갖고 하피넷을 처음에 공부할 때 하여튼 저게 좀 나 그때 뭐 일시적으로는 이건 소프트맥스 이런 건 어떻게 구하? 이건 전혀 내가 배워보지 못한 건데. 라고 해서 좀 약간 그랬다가 하여튼 저게 기본적으로 어텐션이랑 똑같은 어떤 형태 혹은 어텐션의 아웃풋과 결국은 동일하구나라는 것을 좀 이해를 하면서 이게 내가 어텐션을 공부를 덜 했구나 라는 생각을 하고 그랬다는 건데 별로 재미는 없어 보이네. Okay, and and also there is one additional note that I'd like to make. So in this case, when doing this attention mechanism of doing these inner product of the variable length. So for example, the first, within our single batch, suppose the first input source sentence was hi, I am John, and the second one had maybe different lengths of the input sentences. Okay, and in that case, we still need to when computing that attention vectors of doing the variable number of inner products. Okay, in that case, we still use the batch processing. Okay, so in that case, as I briefly mentioned earlier, so we use kind of technique kind of similar to bucketing. Okay, so when doing the attention kind of computation, so we will have these four different input vector, and then maybe the hidden state vector generated just before generating this John, and then we will do the inner product, but we don't implement it as a for loop. Okay, we do the batch processing over there, and also this batch processing is also applied to the next input sequence. So if the next input sequence is like maybe having a five sequence lengths, okay, 5 input tokens, and then we don't do the for loop. For this one, we have to do the for loop of the 4 steps and the 5 steps and so on. We don't do this for loop, and so we actually use a zero padding on that. Okay, so so we actually when computing this attention vectors, which is a sum to one kind of softmax vector, when doing so, we also do this batch multiplication between this entire kind of matrix and kind of aligned hidden state vector and so on. Okay. 이거 이해가죠? 무슨 얘기인지? 네? 그러니까 이게 여기서는 4개를 해야 되고 4개랑의 이너 프로덕을 해야 되고 그 다음 번째 인풋 시퀀스에서는 뭔가 하여튼 어텐션을 구하려면 5개 인풋 시퀀스가 있으면 5개와 각 디코더의 타임 스텝에서의 히든 스테이트 벡터랑 이제 이너 프로덕을 해야 되잖아요. 그러니까 저기서는 4개 해야 되고 저기서는 5개 해야 되는 거죠. 4점. 그러니까 그거를 저기서는 포룹을 해갖고 각각의 랭스별로 이건 1부터 4까지, 이건 0부터 3까지, 0부터 4까지를 이렇게 따로 돌리는 식으로 구현을 하는 게 아니라 저거에다가 그냥 이 맥스 랭스로다가 저쪽 이제 인풋 시퀀스의 0, 아까 약간 센티넬 같은 거를 0을 쭉 채워갖고 어쨌건 이거를 직사각 행렬 혹은 텐서로 만든 다음에 거기다가 그냥 통째로 저 히든 스테이트 벡터를 퍽 하고 그래서 그런 식으로 이제 매트릭스 멀티플리케이션으로 이걸 해결을 본다. 왜냐면 그렇게 코딩을 해야 이게 패러렐라이제이션이 되니까 GPU에서. 그래서 하여튼 여기서도 또 그러니까 뭐 아까 얘기했던 그 인풋단만 아니라 그 저 0처럼 저렇게 낭비되는 어떤 메모리 공간이나 계산들이 끊임없이 계속 발생이 돼요. 하여튼 내부적으로도 인풋 시퀀스가 다 굉장히 다릅니다. Okay, and any other questions? Okay, I don't even know what these slides are because they were not covered in the lecture video. I thought it's completely matching your slide with the video lectures that we study. But let's wrap this lecture. then we haven't even touched the next lecture. Oops. Although we don't have much time, I'd like to mention at least a few things. lecture. 이거 좀. 렉처 10이었나요? 파일명이? 12 맞죠? 11? 스피치, 그거 다음 거가 10이죠. 어디 있을까요? 지나갔어요? 어디 있죠? 이거? 참고로 이런 거를 뭐라 그러는지 알아요? 그러니까 여기서 뭔가 렉처 11을 여기서 찾으려면 시간이 오래 걸리잖아요. 근데 이게 아까 내가 얼핏 보기로 이게 16대 9거든요. 슬라이드가. 그래서 여기서 16대 9라는 슬라이드는 바로 포인팅을 할 수가 있잖아요. 그렇잖아요. 여기서 16대 9를 찾으시오. 그러면 저거 하나가 그냥 바로 보이잖아요. 근데 렉처 12로 끝나는 어떤 스트링을 찾으시오 그러면 뭐 당연히 오래 걸리잖아요. 약간 뭐라고 부르는지 아나요? 그런 게 뭐 그런 거 뭐 있어요. 프리 어텐티브 어쩌고. 프리 어텐티브. 그러니까 이게 뭔가 우리의 대뇌까지 가서 뭔가 프로세싱을 하지 않아도 우리가 뭔가 직관적으로 딱 알 수 있는 그 인지과학, 뭐 이런 퍼셉션 혹은 뭐 코그니티브 사이언스 뭐 이런 쪽에서 약간 뭐 HCI나 이런 쪽에서 이런 거 막 하는데 하여튼 그래서 뭔가 모양이 다른 거 이런 뭐 서로 다른 모양을 딱 이렇게 잡아채는 거는 이게 뭐 프리 어텐티브 어떤 뭐 프로세스 우리의 인지 그래서 뭐 빠른 거고 하여튼 그런 거 있는데 시각학 강의 뭐 이런 데서 이야기를 한 적이 있었는데 오케이. Okay, so related to the attention stuff, I just wanted to mention some additional thing that I I remember I saw in some of the papers in the maybe NLP stuff. So in this case, so these attention kind of examples by following the input sequences from our audio sequence. I mean, in that case, I don't think there is a kind of a case that this attention is actually following the reverse direction. So suppose we attended at this point when generating this, and then suppose we have to generate the next time steps token as a decoding output. But in that case, we know that all the relevant information is only available, only existing in the later kind of input sequence. Okay, because we may not, we may not. I mean, it may not be the case that we look back, right? So there is no kind of reverse kind of direction of these attentions, right? So it is always like this kind of direction. So in that case, so in our attention, so attention will be applied to all the sequence, but in that case, if we want to apply the idea of like attending only to the left, the right one, I mean, although it's a soft attention vector, so it is a little bit difficult to implement this kind of idea, or it's a little bit tricky. But I'm just giving you kind of a simple but cute trick, so that if you want to impose that kind of idea, then you are computing the attention vector, I mean linear transformation output across maybe 300 input sequences, and then you apply the mask on these input sequences. So if you know that we have to attend maybe starting from 100, maybe 101, and then we just make all these values, which is part of or the first 100-dimensional output from the linear kind of transformation, and then we just mask them, or we just replace them as 0, and then using the remaining ones, and then we apply the softmax. Or 0 when doing the softmax with the input of 0, and then it will produce 1, right? So it will not produce 0 probability. So we typically like replace these values as negative infinity. So in that case, even when doing the softmax, these values will remain close to be 0. So that is one kind of trick that I saw in one of the NLP kind of domain papers. So yeah, sorry for being late. So the time's up, so we will cover the rest of the lecture next time, and then maybe I'll announce as soon as possible about the lecture that we have to watch until the next time. Okay, thanks. 네, 수고하세요.
미팅은 무슨 일로 나왔나요?
그거요? 가만히 보자. 그거를 내방에 할 공간이 없어. 아직.
그런가요?
6층에 어디에 가서 좀 하면 될 것 같아요.
네.
그러면 일단은 거기 영실 가 있다가 그리고 좀 내가 찾아갈게요. 네.
교수님 찾아보니까
네.
아까 그 문제 때문에
네.
논문도 나왔더라고요.
그래요?
네. 이 제목이 이런데 이 MLE 대신에 이제 이 NC가 GPU가 안 올라가는 문제 때문에 아예 그걸 올릴 때 구조적으로 바꿨더라고요.
네.
그래서 그냥 그런 문제도 있구나 해서
네. 이게 그러니까 이 강의에서 관련돼서 언급을 한 게 그 같은 논문인지 모르겠는데 이게 그러니까 그 네거티브 샘플을 그 대칭의 모든 이그젬플들에 다 똑같은 네거티브 샘플을 쓰는 경우가 있다.
네.
그런 얘기가 그런 얘기를 강의에서 하긴 했었거든요. 이게 약간 그런 건지 아닌지 좀 모르겠는데.
만약에 그럼요, 그 이 폭이 넘어가면 그 샘플도 바뀌나요? 아니면?
네, 바뀌어요.
바뀌나요?
네. 이 폭이 넘어가면 샘플은 당연히 바뀌어요. 그리고 그거는 바꾸는데 그렇게 크게 우리가 그러니까 시간상으로 손해를 하는 거예요. 왜냐하면 이터레이션은 기본적으로 포룹이거든요. 포룹으로 구현이 돼서 포룹에서 시작 단계에서 우리가 어떤 코드를 이렇게 집어넣을지는 그건 어쨌건 시퀀셜하게 되는 거라서 거기에 뭐 이런저런 서로 다른 어떤 네거티브 샘플링을 포룹의 그러니까 포룹 시작하는 그 안에서 처음에 그걸 하겠다. 그거는 뭐 괜찮아요.
이거 다 자세히 이해를 해보고 가지고
네네 그래요. 네,
감사합니다.
네, 수고했어요.
그 퀴즈에서
네.
NFCC
네. NLPC요?
그 A랑 B 중에 헷갈렸는데 저는 스펙트럼
그러니까 MFCC랑 그러니까 그거를 뭔가 저기 좀 거기까지 강의를 좀 못해서 그런데 약간은 뭐 기본적으로 스펙트럼에 해당하는 프리퀀시 도메인으로 이거를 변환을 하는 그거는 똑같거든요. 스펙트로그램이나 이제 MFCC나. 근데 이제 MFCC는 좀 더 뭔가 더 많은 프리 프로세싱이 부가적으로 더 들어가요. 그리고 이제 스펙트로그램은 그냥 딱 프리퀀시 도메인으로 그러니까 프리에 트랜스폼이나 이런 걸 해갖고 그냥 그렇게만 바꿔놓고 그냥 거기서 끝나거든요. 거기서 뭐 하여튼 뭐 약간 더 하긴 하지만 어쨌건 뭐 거기서 거의 끝나는데 이 MFC라는 거는 뭐 하여튼 좀 더 많은 프로세싱을 좀 더 해요. 그러다 보니까 이제 여기서 강의에서도 이제 몇 번 이야기를 아마 한 것 같은데 이제 raw 오디오 인풋을 그냥 사용을 하는 경우는 성능은 안 좋고 그래서 뭐 미니멀 어떤 프리 프로세싱을 한다라고 이야기를 하는데 그 미니멀 프리 프로세싱이 그 스펙트로그램 그거는 이제 쉽게 구하는데 그러니까 MFCC까지 구하는 거는 그거는 이제 어떤 피처 엔지니어링이 훨씬 더 많이 들어가요. 그래서 이제 예전에 뭐 HMM이나 이런 걸 가지고 이제 했을 때는 하여튼 뭐 스피치 하면 무조건 MFCC 벡터 뽑아서 그러니까 거의 이미지에서 시프트 뭐 이런 걸로 피처 익스트랙션 해서 거기서부터 시작을 하듯이 음성이다 그러면 무조건 MFCC로 변환한 후 거기서 뭔가 시작을 했는데 지금은 조금 더 엔드 투 엔드로 인풋 쪽으로 좀 간 거죠. 조금 더
로우 피처니까.
네, 맞아요.
그리고 그 레이어 그 LSTM도 막 레이어 여러 개 해서 디코더에서 사용을 하잖아요. 근데 그 인셉션 모델처럼 막 중간 레이어에서도 예측해서 로스 발생시키도록 이렇게 하면 좀 더 성능이 좋아질까요?
중간 레이어에서? 근데 중간 레이어에서 이게 슈퍼바이즈할 그라운드 트루스가 어떤 게 있을지 좀 또
거기서도 똑같이 그 텍스트 예측하도록 이렇게 해서
아, 네. 그게 거의 그러면은 그거 구조잖아요. 그 인셉션
네, 인셉션 그거죠.
그런 거죠, 그죠?
네.
뭐 그렇게도 할 수 있죠. 네. 네. 근데 뭐 하여튼 그런 식의 트레이닝 구조가 이제 저기 구글넷에선 쓰였는데
네.
그 이후에는 뭐 레지넷도 그렇고 뭐 이렇게 레이어를 더 많이 쌓았을 때, 그러니까 어떻게 보면 구글넷 이후 레지넷이 나오면서 더 많이 쌓았는데 정작 그런 거는 더 이상 안 하는 것 같아요.
네, 어느
그죠?
순간 이상부터는
그러니까 뭔가
더
레지넷
딥하게는 안 하는.
그러니까 레지넷 같이 이렇게 그러니까 레이어들이 더 깊어졌는데, 그러니까 구글넷에서 이렇게 중간중간 빼갖고 그렇게 이제 그라운드 트루스를 이제 흘려보내서 백프랍을 한 것도 아마 이렇게 레이어가 깊어지면서 저 끝단에서 이렇게 되니까 이게 학습이 제대로 잘 안 되니까 컨버전스도 느리고 이러다 보니까 중간중간에 끼어든 걸 것 같거든요.
네.
근데 이제 레지넷 같은 경우 더 이렇게 깊어졌고, 더 깊어진 상태에서 그러면은 그런 게 더 필요했을 것 같은데 오히려 그게 없어진 걸로 봐서 내 생각에는 그러니까 같이 이제 동시에 뭐 여러 가지 기술들이 개발이 되면서 뭐 나온 그게 무슨 테크닉인지 모르지만 뭐 예를 들면 구글넷을 트레인할 당시에는 뭔가 배치놈이 없었을 것 같지는 않은데 뭐 그때 당시엔 배치놈이 없어갖고 이게 트레이닝이 당최 안 돼갖고 그렇게 했는데 뭐 이렇게 레이어도 깊어지는 그와 동시에 이렇게 뭐 레지넷 같은 뭐 배치놈 같은 어떤 새로운 그 트레이닝을 좀 더 안정적으로 잘 할 수 있도록 하는 깊어도 그런 테크닉들이 나오면서 그런 게 좀 필요가 없어진 게 아닌가 싶은데.
CNN 쪽은 렐루 사용해서 그레디언트가 어느 정도 보존이 되는데
네.
이렇게 버티컬하게는
네.
그 RNN에서 LSTM이나 이런 데서 다 결국에 탄H나 시그모이드가 쓰여서
네.
쉽게 이렇게 하면 좀 더
그럴 수 있죠.
수직적으로도 그레디언트 베니싱이
그렇죠. 근데 이게 또 RNN은 또 나도 그게 왜 그런지는 모르겠지만 하여튼 RNN은 레이어를 깊이는 안 쌓더라고요.
네. 제일 깊게 본 게 8층짜리였어요.
네, 그러니까 네, 그렇죠. 한 2, 3, 4, 5, 하여튼 5, 뭐, 요 정도나 쌓지. 그래서 나도 왜 그런지 잘 모르겠는데. 네, 잘 모르겠어요. 네. 근데 이거 뭐 스피치 이쪽에서도 뭐, 컨브 LSTM이나 뭐, 하여튼 뭐, 지금 스피치 쪽에서도 뭐, 그렇게 very deep convolutional 뭐가 또 있더라고요. 그러니까 이건 비록 스피치 쪽이긴 한데, 이제 뭔가 CNN을 사용을 해서 레이어를 훨씬 더 좀 깊이 뭔가 쌓도록 한 뭐 그런 게 좀 있는 것 같아요. 뭐 여기 보면 제목 자체가 이게 Very Deep Convolutional Network. 물론 이건 오디오 쪽이긴 하지만 어쨌건 이것도 기본적으로는 RNN 구조이기 때문에 그래서 뭐 이런 경우는 뭐 비록 이제 CNN으로 대체를 하긴 했으나 오디오 시그널이 굉장히 로우 해갖고 하여튼 내가 보기에는 그 워드 인베딩이 어느 정도 좀 그러니까 그거 자체도 어떻게 보면 피처 익스트랙션된 어떤 그 토큰에 대한 피처 레프레젠테이션인데 그거 자체가 꽤 그래도 좀 이미 많이 뭔가 다 정보가 하이 레벨 정보들을 많이 담고 있어서가 아닌가 싶은